Why do we have a tray?
This meeting is being recorded.
Well, that was aggressive.
Okay. Okay, I'm gonna start. What are you laughing about? You laughing at the title?
I'm not laughing at you.
No, you can laugh at me.
I'm laughing at the automated voice,
Oh,
like screaming about the recording.
You've never heard that before?
Well, I
uh,
heard the first one, but the second one.
okay, I'm gonna start. So this is the title. This is a recap of the last 6 months of my life that have been, equal parts terrible and wonderful. I don't know, whatever.
What's the seven circles a reference to?
Dante's Inferno.
Oh.
Yeah. So the TLDR is this, which is completely unintelligible to I think everybody on the call, but I will come back around and explain this, and hopefully throughout the course of the presentation you'll figure out what this means and be highly impressed. So this is the outline of the talk. You asked what's the title in reference to. This is flexing my erudition. This is the cover of the 1590 release of the book Dante's Inferno. Anyway,
Yeah, I mean, he's taking some artistic license.
me, or you mean because I've macroed it? Yes, I'm an artist. Yeah. Okay. So these are the seven circles of hell. With all due respect to Nick, I guess the first one who works on PyTorch, the first two are purgatory, really not actually hellacious in any way. Anyway, another fancy word. So this is like background. The background to this project is, hey, there's this science experiment, X-ray crystallography. The way that it works is high energy electrons or X-rays or whatever are shot at some material. They're scattering. According to Bragg's law, you take measurements and they can conclude certain things from whatever the distribution of peaks is in the XRD or XRF plot. The important thing about these experiments is that they should happen very quickly, right? The detectors need to work really quickly. And if they don't, you're going to get a bunch of data. So sorry, backing up. The detectors have a sample rate, have some fixed sample rate. Currently, the sample rate is 3,000 hertz. So they're reading the entire black CCD, that's a camera chip, 3,000 times a second. And that's basically fine. They can keep up with it. They store the data, post-process it later, et cetera, et cetera. The next generation of detectors is going to ramp it up to 1 megahertz, so 1 million samples a second. And at that rate, you basically can't dump data off the device fast enough, given current limitations on like PCIe and stuff like that. So the idea is to handle the data in situ on the chip. So there's prior work here. There's at least 2 prior papers from Argonne. One of them is this thing, Bragg and N, which tries to do things really fast using a neural network. The other is in silico compression that lightens the load for downstream processors by compressing the data. Okay, so that's one prior work. The other prior work and the neural network angle to this is I want to use a neural network to do basically anomaly detection, like 0-1 classification. Hey, is there anything interesting in the image or not? Why would I want to use a neural network? Because the classical methods for figuring out if there's anything interesting in the image, these pseudo Voigt distribution fitting methods are too slow. So what you have to do is you take a look at this distribution, which, where's my mouse? What do I want? I want a pointer. Where's the, you can see it?
Yeah.
Oh, okay. So this is it, right? This is a distribution, X, Y, Z is a height. This is a probability distribution called the pseudo Voigt distribution. And if you can fit such a distribution of the data, then it's an interesting sample, keep it. And if you can't fit one, ditch it. Don't store it. Don't leave it around for later post-processing. So that pseudo Voigt distribution fitting is really slow. Everybody wants to throw neural networks at something. This paper demonstrates that they can do this 200x faster than the classical method. So the goal, so 200x, I haven't said where we're starting. I have said where we're trying to end up. We're trying to end up at being able to make a detection 1 microsecond in 1 microsecond. So the collection rate is 1 megahertz. That means I need to make a detection 0-1, give an answer in 1 microsecond. So this thing, I don't know. I don't know where it starts and I don't know where it ends, but let's just peg it at like 100 microseconds. So it's still 100x off. So the goal is to go even faster. Goal is to go 100x faster. So neural networks run on quote unquote accelerators, purpose like domain-specific processors, GPUs. What can we do with even more specialization of the hardware deployment platform? Okay, so the target here for the project is to deploy to an FPGA. You know, what the hell is an FPGA? This is like a high-level overview. It's a fabric of really atomic, fine-grained units of whatever compute. So this is actually a really good picture. It's one of the best pictures I found. The only thing that you should take away from this picture is, hey, it's laid out as a grid and blah blah. The next picture will actually tell you, give you a better idea of what it is. So this, by the way, is like marketing promo material from Xilinx. This is a picture from my, like, hey, I have the IDE. I pulled up the diagram for the actual FPGA that's a target for this whole project. And on our side, the screen is really whited out. But over here, you have basically like adders, ALUs. So that's what a DSP is. A lookup table is something that you can use to implement really simple functions. So like 6 inputs, 32 outputs. Multiplexers combine signals. Flip-flops are literally registers, 1-bit registers, and ripple carry adders are, hey, some way to add things. So one of the cells in this picture, it's here, right? It's like at the lowest level of this hierarchy is this, and then that corresponds to this part of this diagram, and you connect them using routing resources, right? So you have this grid of, you know, resources, really, like I said, atomic compute resources, and you can connect them in interesting ways. There's a lag. Why is there a lag? I have already flipped through 2 slides. Okay, cool. So how do you program, quote unquote, program an FPGA? The P in FPGA stands for programmable. Program is actually a misnomer here. You do not write code for an FPGA. You design circuits. Traditionally, right, before what an HLS, and I'll define HLS in a second, before HLSs came around, it's just digital logic. It's just digital design. And they typically use like CAD tools. So the CAD, computer aided design, is a phrase in this area. EDA, electronic digital assisted design, whatever. So about like 10, 15 years ago, people started researching how to translate high level specifications for various things into these digital circuits, and whose specification is, by the way, called RTL. There's a lot of acronyms in this area. I don't know why these people love their acronyms so much. HLS stands for high level synthesis, which means I'm going to take a really high level description of something, some, you know, like process, some code, some task, whatever. And I'm going to translate it, lower it, interpret it, whatever, into RTL, which stands for register transfer level description. So these designs, these digital designs, literally specify this register talks to this register, this wire connects these 2 registers, et cetera, et cetera. So you're not coding, it's not imperative code, you're designing. And these tools, they claim to help you, they claim to basically magically do this. Most of them work on C++. I think that there are basically no actual commercial solid HLSs that work on anything else, like Python or anything, despite what people you will find on GitHub, whatever. So about 1.5 years ago, this company Xilinx, which is so there are a couple of manufacturers in this area. Xilinx is the big one. Intel's another big one. Opened up an API where you can pass in something called LLVMIR. So this is the path that I'm taking. I have a description of a neural network. I'm going to do a bunch of stuff to it. I'm going to get LLVMIR. I'm going to feed it to their HLS tool. And out, in theory, in principle, you hope will come out a description of a circuit that goes really fast. Okay, at some point during this talk, invariably, you're going to be like, Max, why did you do this? Isn't there some alternative? Why did you reinvent the wheel and the cart and the donkey and everything? I guarantee it. I mean, I said this to myself many times. So there are a bunch of things that claim to be able to do this. This one's interesting because this is, I think, the famous project that Ian's really like charmed by, where he apparently like gives, you know, like this is some kind of soundbite or pull quote where he's like, oh, they used heterogeneous blah blah and deployed to the cloud FPGA stuff. This is the team that he's
That's the
talking about.
physics guys, the hip
Yeah,
guys.
exactly. So this is Fermi, UCSD, CERN, whatever. So I don't know. I don't want to talk shit. I don't want to like.
You are being recorded.
Yeah, exactly. Which is why I don't want to touch it. These alternatives, yeah, 100%. I mean, I have no ill will against any of these people, but these things don't work. So these are not really alternatives, and I can explain why, but at this moment, it wouldn't be really like intelligent. These are abandoned, there's a ton of abandoned projects that look like they could do something like this. They don't do it. And by the way, this one is the whole porcelain. Yeah. The closest that you can come to doing what I did, and these are honestly way better projects. Like I'm not trying to take away anything from either of these two groups. So this is one guy at UIUC. This is a couple of people at PNNL. This guy Nicholas Augustini. Unsurprising, they're both going through MLIR, which I'll define later. These are kind of like similar. I'll explain how they're not because I've charted my own course. Okay, so they're like young people, like I don't know how many people are, in our undergrads and how many people are in high school and the DSI students. I think it's important to point out, like I put together this presentation linearly, like the narrative here is pretty linear in order for it to be intelligible and enjoyable. It did not look like this over the last 6 months. This is absolutely what it looked like. Kyle can attest to this. He was my therapist at many points over the last 6 months. And it wasn't until like 3 weeks ago that I actually was, knew that I could pull it out of the hat, out of the bag. So, okay. So the first layer of hell, which is not hell, it's purgatory, is PyTorch. So on the left, you have representation of Bragg and N. This is basically 5-star art. I didn't draw that. I actually stole that from Edward Yang, who nicknamed.
The little doodle you stole?
Yes.
That.
Yes. Good. What is it like? What did Jobs say? Great artists create. Sorry, good artists create. Great artists steal. I'm not above stealing even the smallest bit of thing. And a lot of this project is actually lifted from open source. But anyway, okay. So here's some representation. This is pretty recognizable if you write Python. This actually isn't Python. This is like some serialization of the model. This isn't code, right? This is like you print the model and it prints this stuff out.
Just so
Yes.
that so Bragg and N is your neural net that
Does detection.
emulates that
Yes.
thing that's too slow.
Yes.
But Bragg and N is an order of magnitude too slow.
Yes. 2 orders of magnitude.
Okay. All right.
Yeah.
2 order. Okay.
Raph, can you mute yourself as well?
So
It
you're
sounds
trying
like
to
you're in a
make-
coffee shop.
And you're basically trying to.
Oh, sorry. I thought I was muted.
Yes. Yeah.
All right.
Yeah, that's a good way to put it. I mean, yeah. So that's why the winding path goes from PyTorch to
Yeah. All right.
yeah. Okay. It's weird lag. Anyway, on the left you have PyTorch. Adit asks if the left is TensorFlow. It's not. It's PyTorch. It's not actually PyTorch. Like I already said, it's a serialization. Like repr of the model. It's not actually. Anyway, on the right, and this is my stump speech at this point. If you don't know what's going on the right, like, and you're in deep learning, you're gonna get left way behind in the next, like, I don't know. I'm like really new to this kind of stuff, so it's pretty arrogant to make some kind of statement like this. But you're gonna get left behind in the next 5 years as every like mainstream neural network framework moves on from eager mode. Although TensorFlow was statically defined in the beginning, but so maybe in particular I'm talking about PyTorch. But there are other deep learning compilers. Almost from what I can tell, almost all deep learning frameworks are moving on from eager execution, eager specification to some kind of like 2-level representation modality where maybe you do your experimentation, which is how eager mode was originally intended to be. I think you do your experimentation in high-level Python, eager execution, and then you export the model. So this is PyTorch's homegrown intermediate representation. I've highlighted the parts that correspond, left and right. Hey, I got a convolutional filter on the left that you can read easily. On the right, it looks like this. So the words are a little bit different. There's these percent signs, but it's a representation. And the point is that it's a more easily like statically analyzable. It's a really bad like neologism, whatever, representation of the model. And people use this to deploy to various architectures and do other interesting things. Slice and dice the graph, which represents or is represented by the left, and do things like pipeline parallelism. Okay, so that's a sum speech. You're going to see the percent sign everywhere. Percent means some variable name that is only assigned to once. So that's what SSA stands for, single static assignment. And in the community, people think of it as a register. It's not actually a register. It's a, whatever, call it a virtual register. It's not actually a computer register. It's a single assignment variable and no mutation. You can't mutate them. Okay. Okay, so that's where you leave purgatory and you're actually entering hell. MLIR is actually a pretty good framework. Like, it's really like commercial grade, weapons grade compiler technology. It's very, very good. It's getting mature quickly. There are a lot of people jumping in. Google, has parts of it. I don't think actually Facebook actually, I found something just recently. They're implementing Clang dialect, whatever. So people are jumping on this. This is what the bulk of the work was, or I say half of the work. Half of the work was like managing MLIR. So what is MLIR? Again, some people might not know what an IR is. The thing on the right on the previous slide is an IR. Intermediate representation, that means in between your Python and your actual assembly instruction set on your hardware. So, it looks a little weird. The thing about MIR, so there are lots of IRs. If you look at something like this, it's linear. There's no structure. It's a data flow kind of thing. There's a graph implicit in this. There's no for loops. Sorry, there are for loops, but the way that IRs typically implement for loops is using jump and branch. So if you look at LLVMIR, I can't remember if TorchScript does this, but if you look at LLVMIR, the way that a for loop looks is you're going to execute 10 lines of code and you're going to get to a line of IR, which is going to be a compare against, hey, is this something less or equal to 10? If it's less or equal to 10, jump back to the top of those 10 lines and do it again. So this is a way to represent a for loop that works and that the IRs typically use. MLIR, trying to be more modern about certain things, lets you represent for loops in this way, which makes it look pretty nice. Has advantages. There are other things that MLIR does, but I think the principal advantage of SCF, the SCF dialect, is, hey, it's readable. Okay, so there are a bunch of the way to like grok this or read this is the things before the period are the dialect. There's a grouping of concepts, symbols, whatever, under some namespace, under some, I don't know, conceptual umbrella. So the for loops are under the structured control flow umbrella. Structured here means, hey, there's indentation. That's basically what it means. There's the memref dialect, which captures ideas around memory that has reference semantics. That means if I do something to that memory, I'm going to mutate something somewhere else. It's not value-based semantics where if I mutated, I get a new value after the mutation. I can change things in a way that is like technically not kosher for intermediate representations because I said, SSA is single assignment, no mutation. Anyway, and then there's the arith dialect, which just, handles things like arithmetic, like floating point and integer arithmetic. So not shown here, but, plays a really important role in all the nonsense that I had to do were the lineage dialects and the lineage and the affine dialects. Okay. So what's the game plan for making things fast? Here's a representation. I actually had a representation of Bragging in like December. Like it took me 2 weeks to wire all the things up and get some representation that could then be fed to these HLS tools to get some circuit. And I presented on this, and like the key thing there were 2 things there that were a problem. First of all, I couldn't talk to it. Like I couldn't get like IO with the board and stuff like that. And that was a pain in the ass. But more importantly, it was slow. So you have to do things. You have to learn how the tool works. You have to learn how to use it effectively. You have to also learn what are the things about particular, ways of formulating problems and writing code that make them fast. The standard thing, just like lowest hanging fruit off the tree, unroll all the loops. What that means is here you have 6 nested deep loops. So this is this is a convolution. This is the real workhorse of the convolution. This is just loading the bias into the the location that'll eventually store the result. So this is like initialization. This is the actual work where you have some kernel that is being read from, multiplied, and then stored back in the whatever. So unroll all this. You get what? I don't know. I actually worked this out. It's like 180,000 or something like that lines. What I mean is, hey, copy paste this body this number of times and then update all of these identifiers to be unique. The reason, so this is like, so unrolling loops, in addition to tiling loops and fusing loops, are like the bread and butter of, yes, exactly like that. That's correct. Are the bread and butter of performance optimization for, whatever kind of code, numerical heavy code. So that's what I did. That was the thing that Vitis wasn't doing. That's what I did. That was the approach that I took, right? Here's a joke, here's a gag, here's a meme. I'm
I don't
gonna,
understand this joke.
because you're old.
Could be.
Yeah. Some people must understand it. Pokemon, right? Like, really? Am I that old that people don't even, that when I was a kid, I played this and now nobody knows about Pokemon? People know. Whatever. This is a good meme. Thank
I
you.
agree.
Thank you, Ari.
Send it to Tyler.
Yeah, okay. So I'm gonna
Tyler will enjoy it.
I'm gonna unroll. I'm just gonna, so this is the thing that I've been saying for months now. When somebody asks me, what are you doing? And then, invariably the person, after I tell them this, they're like, you're insane. Because it's dumb. It's dumb. It doesn't work. It does not work in any other case where you have a limited number of like registers and, circuits and ALUs on a processor, a regular processor. You can't unroll the loops like ad infinitum on an x86, whatever, Pentium M1 GPU, NVIDIA, whatever. But you can do it on an FPGA. Okay, so how many do I get? This is missing. No, it's not missing. There's a fade in. I didn't even know I had a fade in. So how many arithmetic operations are there here? This is kind of like a pop quiz. I mean, it says pop quiz, right? So there are a couple obvious ones. So what I'm trying to get at here is, what does this turn into? How big of a mess do you get yourself into if you actually do unroll all the loops? It's not updating. There's a lag. The stupid transition. Okay. So, right, just like I said, multiply all the loop bounds. So these loops, you can read them as like, and there's another slide which shows them as Python loops, but basically, this loop runs once, this loop runs 64 times, this loop runs 9 times, once, 3. So just multiply them, right? And then count the number of operations in here. So there are 2 integer arithmetic operations, there are 2 floating point operations. In total, that's 186,000. So if you unroll the convolution, minus these loads and stores, which do get copy pasted, you have 180,000, and you can multiply by 2 to get the total number of instructions. But what you're really thinking about is, how many compute intensive operations do I have to do? And that's the number, and the floating point ones are more compute intensive than the integer arithmetic ones. Okay, so here's a bonus question. It hasn't updated. Are there any others? I'm going to pause here for like 10 seconds because this is a fun trick question. And I don't know if Ryan's on the call. I guess not. I did tell you, Kyle, at some point. It's fine, you forgot, because I've been saying a bunch of things over the last 6 months. Can anybody venture a guess about whether there are any more? And none is a this wouldn't be an honest pop quiz or extra bonus point if none wasn't an option. So Nick can't answer.
What about all of the loops?
That's true. That's a good one. So what part though?
The addition
Which
and the equality. So like
you mean the compare? So yeah,
Yeah.
I'm going to take the words out of your mouth. What are you saying?
the comparisons. So like checking if you're unrolling the loops, and probably even if you're not.
Let's talk
Compare.
about it. Who are you?
Oh, audit.
Audit. Cool. Yeah, keep going. That's good.
So probably like both incrementing the values of
Cool.
like
Yeah.
I1, I2, I3, I4, I5,
good.
I6, and then
That's good.
also like equality.
That's good. Yeah. So the compare, the jump not equal or jump if equal instructions are definitely inserted by, like, for example, if you lower all the way to LLVMIR, that's the comparison that you're talking about. The constants are actually inlined. So like the loop is unrolled and there's no increment. The constants are inlined. You actually just count out, because you can do that. You know which values I4, I5, I6 take on. You don't actually need them. You do need a comparison though. I might be wrong about that, but it doesn't matter. That's a good answer. It's a very good answer. There's another one. Okay. In these slices, which again are like a nice feature of the intermediate representation that MLAR gives you, these are like we are all very, very comfortable with slicing arrays in Python. There's no such thing as a 4-dimensional block of memory, right? These are translated into linear offsets in linear memory. And there are, so I had like a little bit of arithmetic, just like this one, where I had an equal sign and the product plus flag. And of course, as soon as I get, okay, anyway, I had a slide here that said, oh, it's this many, it's this many. There's a certain path that you can take through this chain of whatever lowerings, they're called lowerings, where this does show up in the final IR. There's another path where it doesn't show up. So that's why I took that slide out as far as counting it. You know, so the point here is don't get too comfortable with like your high level abstractions. You're paying some amount of cost for those high level abstractions, which is like another one of my stump speeches. So I will say though, you know, I don't want to mislead anybody. Integer arithmetic is way cheaper than floating point arithmetic. It's not free. More important, so it's not free on conventional hardware. It has some cost. Maybe it's like 1 cycle, 2 cycles. Floating point, depending on the hardware, is some extra number of cycles. That's not the problem for me. I'm not running on x86. I don't actually care. I mean, I don't care, at least at this stage in this journey into the 7 circles of hell. At this stage, what I care about is, hey, sorry, I lost this. Yeah, okay, right. So I have this thing. At this stage, what I care about is how many lines of IR do I have? Is it too much for the downstream HLS tools? Because what I ended up running into was I would unroll these, and you can unroll them if you just naively unroll them. And I'll talk about what you have to do to not to, you know, in a more sophisticated way to unroll them. And the tool, one particular tool, Vitis, just never, well, I don't know what's going on. Yeah. Vitis, this thing from Xilinx that you have to use that I used until I understood the, you know, until I became, while I was a Padawan, whatever, will just die, like choke, like take forever. If it ever finishes, it never finishes. I was sending, you know, these screen caps to Kyle and Ryan, like, oh, it's at 36 hours, it's at 50 hours, it's at, and then it would OOM, you know, sometimes it would OOM, I had to get more RAM and blah, blah, blah. So what is HLS? I brought up HLS before. What does HLS do? Because I eventually had to like bite the bullet and be like, this thing doesn't work for me, for my edge case. Maybe it's wonderful for most conventional people. Like I said, when I told people what I was doing, they're like, you're insane. This is a far, far edge case. This is the edgiest case. Unroll everything. What does HLS do? HLS takes your high level representation of your thing, and it does 2 things in primarily. I mean, it does whatever else, but it constructs a schedule of the operations, which operations run during which clock cycle. So, right, so on FPGAs, you set the clock cycle. Your M1 runs at 2 gigahertz or whatever, your i7 or i10 or i9 runs at 3 gigahertz. Something happens on every click of the clock. FPGAs, you control all that. That's your responsibility. The way that, so you have to construct a schedule and you have to construct some control logic to like transition from first doing the scheduled stuff that was the first thing to doing the next thing to doing the third thing. And that's an FSM. So it builds an FSM. The construction of the FSM is pretty straightforward once you have the schedule. So the hard part is really the schedule. And then the second thing it does is it connects your scheduled operations to actual hardware. They're called IP blocks, but just think of them as hardware, you know, collections of gates and registers that'll do multiplication, addition, whatever. So I had to rebuild this because this is what I said, right? Like I would sit there and I would, this happened for weeks. You guys, why can you see my entire screen? I can't pull up the notes. And now you can see this, and now you can see this. Great. Whatever. Okay, so yeah, no notes. Anyway, so this is, I would go to bed and I would be like, I got it. I did it this time. And for 6 months on end, I would wake up and it would be broken or not done or failed in some other way. So 3 months was Vitis failing, and then the last 3 months was the next thing failing. So I had to rewrite it. There's no choice. Just to give you an idea of what this thing, and I went to the next slide. It hasn't updated. I don't know what's going on. Why is this happening to me?
It's a Zoom.
Who's on Zoom?
They're all on Zoom.
Get off Zoom. Okay, yeah, great. So just to give you an idea of what's, so this doesn't have the heaviest weight, quote unquote, passes, optimization passes. This is just like, I made this weekend, just like an example. It should illustrate what's going on. Just a copy, paste, unroll, nothing smart. I'm gonna, like I said, copy paste the body of the loops and update the names of the variables. Takes 17 minutes. So this is seconds and this is 17 minutes for the for full Bragg and N. So the line here is, this is a kind of a crappy chart. The lines here are run times and the bars here are instructions, the number of instructions. So that conv2d has ultimately 217,000 instructions, entire Bragg and N. So this is all being unrolled, not in LLVM, this is being unrolled in MLIR, 10 million instructions to get from the original representation, which is probably like 100 lines of Python or 100 lines of that SCF dialect with the nicely indented for loops, to the final fully unrolled thing where, like I said, you're just copy pasting 16 minutes. And that would be fine. I would be totally fine with that. This is not what, so the problem is that this is not what Vitis does. Vitis does, it tries to do smart things that take way, way longer. At some slide, I was going to mention this, I guess, but I can't see my notes, so I'll just mention it now. The problem with Vitis and the proprietary tool is it's a black box. I know roughly what it's doing from the papers that went into implementing it, because that project was purchased from some research group in UCLA. And then they've published some follow-on papers, and then you just ask people and you like grapevine type stuff. So I roughly know what it's doing, but I don't know exactly what it's doing. And more importantly, I can't control what it's doing. So I enrolled all the things and I simplified all the things, and it would still take forever because it was redoing some of the work, but I'll get to that. Okay, so it takes forever. Why does it take forever? The naive unroll of the Bragg and N, it's naive. It doesn't do some things that are kind of like, again, low hanging fruit, the next stage of low hanging fruit. And so this is a pop quiz. Does anybody notice anything? I know it's hard to, like, there's a lot of visual noise on the screen, a lot of percents, a lot of X's, a lot of angle brackets. Probably nobody's going to notice. They don't know what they're looking for. Does anybody notice something wacky, a little bit wacky, I would call it? It's fine to say no. Yeah, okay. So what's happening, and the next slide highlights it, is that there's a funny thing that's happening, a weird thing, given a high level understanding of the task at hand, right? Not from the perspective of the computer, not from the perspective of the compiler, but just like, I'm a human being, I want to do X, I want to accomplish Z, whatever. What's happening is this weight, sorry, this current value for whatever convolution that you're computing, right? So you can imagine, hey, I have a 3x3 window. I'm going to multiply every pixel in that 3x3 window by some 3x3 window in my image. So you could do all those multiplications in theory at once, right? None of those depend on each other. And then you can actually do, so if it's 9 by 9, you could do like 4 additions. So you sum to 4. You have 9 products, and then you want to get one number out of the end. So you combine, and it's like a binary tree, blah, blah. I have a slide on this actually later that I use this fact. But anyway, in the naive unroll, what's happening is you load from your current storage place, you update, you do some arithmetic, and you update. So load, store, load, store. This is worthless. This is like, as far as the instruction count, literally just lines. Like, it's useful for CPUs that have memory banks, that have caches, that have whatever. That's reasonable. I'm just, at this point, I was not thinking about architecture. I was just like, how do I reduce the line count to get through this thing, get all the way through? And so what you do is, and this isn't some brilliant observation, like I could have just like read a compiler book more closely and knew it ahead of time, but I was looking through these things and I just noticed it. But of course, everybody knows this, right? And so there are things to handle this. So the like broad term for this is store, load, forwarding. You want to take those stores that are unnecessary. Don't store the intermediate. Over here, where you're like, I'm gonna, this value, this, you know, %9 is the result of take the current stored value, do some arithmetic, and hey, I'm gonna now update it. Don't do that. Just ditch this store. Ditch this, so keep the 9 around for the next iteration. Of course, in a for loop, you can't do that because these look like they're being updated. But when you're unrolling, hey, I'm just gonna keep I'm not gonna load. I'm just gonna use this number, this 3002. Wherever I have 3005, I'm just gonna replace it with 3002. That saves me, I don't know, like 1/10 of instructions. At this point, I was like scrambling, clawing for any kind of way to get through Vitis. So there are these passes. The top 2 are in LLVM. The bottom one is in MLIR. These things, they look great. They look like it will simplify the graph. It'll rewrite loads and stores. It'll like make you eggs and coffee in the morning too, right? The problem is that when the compilers are conservative, so the slide hasn't updated. Compilers are conservative. They prove things in order to prior to making the transformations. So if you want to do this store load forwarding, you have to prove, hey, there's no memory dependencies. There's no like stepping on one section of memory by the follow on load or store or whatever, all this kind of stuff. That I'm not reducing numerical accuracy or changing the correctness of the program. And to do that, you have to solve a constraint system. Like if it's a for loop, hey, the bounds of the for loop are such, the iteration space of the iteration space of the for loop is such, the memory space of the memref thing, the reference memory view of memory is as such. And it could be weird, right? Like, so in modern deep learning, you got strided memory and stuff like this. So these things can get really complicated. And what they do is so this is from MLIR. And this isn't like, I didn't have to dig for this. This is at your fingertips. If you do the loop unroll, which is like a standard, hey, there's nothing, this is on the front page, just do it. And then do the scale rep, store load forwarding, whatever you want to call it, and pass a debug flag, you will see all this dump. You will see all this printout. It is checking for this, like the validity, formal correctness of this procedure. This shit is what it takes eons. And I can explain why, but I will say I'm not 100% sure that Vitis is doing, but there's nothing else it could be doing. And so it must be that this is the thing that it's choking on. I could ask somebody, but I know beyond the shadow of a doubt that this is what it's choking on. It's doing its own data flow analysis. It's doing its own, and so it has to check these. So the way that this is solved currently in MLIR in 1 or 2 ways. These constraint systems, you either do like Gaussian elimination, actually like a fancier thing called Fourier-Motzkin elimination, but it's basically like Gaussian elimination, or you use an integer solver. That thing's not actually plugged in. Anyway, these are small systems, right? This is a matrix. You can think of this as a matrix with constraints, and you got to do the linear algebra thing. It's got like 10 lines. How long did that take? It doesn't take very long at all. The problem is, one, in general, right? These are integer constraint problems. In general, this is NP complete. So NP complete tells you whether it's solvable or not. NP hard tells you how long it takes, whatever. So the solution is to forget about it. I wanted to say one more thing about this, but it slipped my mind. Anyway, so this has been the progression of my life in the last 6 months, where like I'll be using the tools at the level of like my understanding, and I'll hit a like just brick wall, just complete like 24-hour, 300-hour runtime brick wall, and it's a brick wall because it doesn't finish. And also it's not opaque. It's not transparent. I have no idea what's going on. They're proprietary tools. There is an HLS that is open source from some university in Italy. It basically has the same problem. And I'll just use the excuse that their code base is really hairy. And so I didn't try to investigate why. You push through the wall by like going around it, you rebuild things. Okay, so what's the solution here? This is the thing that I said to you, Kyle, is going to be potentially the core of whatever I dissert on. So this is not brilliant by any means, and I also didn't come to this from some principled place. I just like, hey man, MLIR is kind of annoying. There's a lot of boilerplate. I would rather fiddle with this stuff in a simpler, less like heavyweight language in Python, right? So I'm going to smuggle the IR out. I'm going to smuggle the representation of the thing out of MLIR And this is a patently weird thing, right? Like I was telling somebody about this and he's like, why would you do that? And initially it's kind of a goofy thing. You wouldn't want to do this, just use MLIR in some way to do what this was, I ended up making this thing do. It turns out to be pretty neat. Anyway, a lot of vague words. Okay, so the trick here, so this thing is called abstract interpretation. Again, a really, really fancy word for basically taking this program on the left, which has some semantics, it has some understanding. Hey, this is arithmetic, right? The add I, that's actually arithmetic. The memref.load, that's actually a load for memory. Those are the semantics of the program. And just completely reinventing them, flipping the script, just doing whatever the hell you want. So these memref classes, they're not pointers to anything. They're my own, just like I have changed the rules. This is Bizarro land. These are the things that'll help me accomplish what I want. But just to like explain a little bit about what abstract interpretation is, means reinterpret the program as you see fit. People do this. This is a kind of known thing. This, used in certain projects, whatever, to do. So Julia, for example, uses this to like infer things about types. I don't know. They have some blog posts about how they do abstract interpretation and can do interesting things with types. This is kind of like a cute thing that occurred to me. Again, I did not know this. Like this idea didn't come from this theorem, like some mathematical, like, oh, I solve all my problems using math. But in retrospect, hey, this program, if I want to do stuff to it, so some people ask you sometimes, what's the difference between an interpreter and a compiler? And most people don't have a really good answer. I never really had a good answer. Because it's a gray area, like, oh, both of them translate from one representation to another representation. Compiler will translate, ahead of time, statically, at one go, whatever. But ultimately you get put in a program, get out of program. The output of a compiler is like x86 instructions, assembly, whatever. The output of an interpreter, like in Python, is Python bytecode that then gets, again, run, and ultimately translates to assembly. So like, what's the difference between an interpreter and a compiler? Why call them different things? Why not just say they're all compilers? The answer is, and I think this is kind of like interesting, is a compiler has to prove things. It has to solve math problems before it'll, make transformations on your program. An interpreter doesn't have to prove shit. Just it runs and then chokes, and it's up to you to decide whether the output is correct. And I'm not talking about like the type system or duck typing or anything like this. I'm just saying that an interpreter will run through your code and have no knowledge in some cases, right? Like, so if you have something fancier in the mix, like a JIT or whatever, I'm just talking in like the simplest understanding of an interpreter, it'll run through your code and just do what it wants. And these two things actually formally, in some certain sense, are equivalent. You look up this on Wikipedia, and it's a kind of like computation automata theory thing. A program is a proof, and vice versa. Okay, anyway. So what does my abstract interpreter does? The simplest, and this is the reason you're like, this is weird, this is goofy, why'd you do this? It just prints, right? So these, so again, my cursor is frozen. The teal, that's arithmetic, right? Integer arithmetic. Those are evaluated. Those are actually, those pluses, because they come from a 4 range loop, the VI3, VI6, those are just numbers. Those are just evaluated by the Python interpreter. The green and yellow are not, right? So Python has this nice thing where you can overload operators. So the green, I have, so these are values. They come from this value class. They're instantiations of a value class. And the multiplication just prints something. So print op is like something that I stub out, and I have actually like 5 different emitters. I can print LODMIR, I can print C++, I can print MLIR, which is weird. Again, weird. Why would I export from MLIR and then use this thing to print MLIR? Anyway, whatever, I'll get to it. So the yellow and the green, that's where you see this abstract interpretation. I'm not doing addition. I'm not doing multiplication. I'm doing something different. I'm printing. Cool. Again, really standard stuff. PyTorch does kind of things like this in Dynamo, whatever. So that's whatever. As far as the loop unrolling, whatever. What I'm doing to implement effectively store load forwarding is that these reads are not reads from memory. They're reads from a hash map that just stores values. And when I set, so the reads pull from the hash map, and the writes create new values or they pass values along. So these memrefs end up being, I'm calling them geometric symbol tables, whatever that means. They end up being symbol tables. They just store the most recently inserted value, and value is this abstract thing that like captures the previous execution, blah, blah. I'm not losing any of the data flow. The really useful thing here is that I end up using this in particular to capture the data flow all throughout Bragg and N. So this is like the interesting, useful, generic part of it. You can't do this. Nobody else is doing this. Nobody's capturing data flow all through the entire specification of the neural net. People have hacky implementations of like, well, a convolution carries data from here to here, and it's like handwritten. So Dace, that Torsen thing, he's got his implementation and he's specified. He's not inferred it. He's not like statically, and I'm not statically doing it. I'm doing it this way, but whatever. Okay. So there's a couple of these slides, right? So you're like, great, now I have store load forwarding. I have this really simple representation of the neural net. Everything should be great, right? Like, no, of course not, right? Like, again, it's a black box. I have no idea what is tripping over. I have made it as simple as possible. Like, I can look at the IR, there's nothing in there except values, like just, hey, fixed values that are carried through the program and then are arithmetic, right? Like literally when I was at this point, it was fused multiplications and adds, and it was like, whatever, 150,000 fused multiplications and adds, and that's it. And it's doing something, it's doing some kind of analysis, it's still taking forever. So you're like, Max, are there alternatives to Vitis? Maybe you're, myopic, tunnel vision, ditch Vitis, something else will do better. There are alternatives to Vitis. So Intel's a FPGA manufacturer that produces FPGAs that are big enough to hold this thing. It has Quartus. There's no way that it does anything better. And I asked Kazutomo, I asked this guy at Microsoft. Microsoft primarily uses Intel. There's no way. They do the same things. They all borrow and steal each other's ideas anyway, but beyond that, they're compilers. So they have to do correct things. There's this other company. So sorry, are there other HLS tools? The answer is yes. There are these 4 of them at minimum. These 2 are commercial offerings. It's interesting. This one is purchased. So like Vitis was purchased from some student at UCLA. The project is called Autopilot. This thing was from Toronto, was called Leg Up. These dudes are, these whatever vendors are like highly anti-competitive purchasing these things. Panda is an open source. Panda is the open source one, which is like great. Honestly, it was like emotional support or something like that, where I would run stuff through Vitis, have no clue what's going on, completely Kafka-esque experience, and I would run it through Panda, Bamboo, whatever, and at least it would give me error messages. At least it would do more prints, and I know that it's doing the same thing basically, so I have kind of some sense of what's going on in Vitis that's crashing or stalling. Catapult, this one's interesting. This one might work. I don't know. To be honest with you, I have no idea. This one is reputedly the best in whatever. This is from Simons. The license is like $1 million per seat. Yeah. Okay. So I have to ditch Vitis. What do I have to do? I said this before. There are 2 things. I will never forget this.
Just kidding.
Just kidding.
It's recorded.
I'm just kidding. You're not gonna watch it. Don't even.
I actually am waiting for the punchline, so.
We'll see him do the last one.
Yeah. Yeah. Okay. So I had no idea about any of this stuff. So by the way, just like a quick, Kyle, this, I don't think anybody really believes me. I had no clue, I did a legal decree in front of children. I had no clue what the fuck I was doing 6 months ago. I had never seen LLVMIR. I had watched one 30-minute presentation on MLIR. I had never touched an FPGA or whatever. And I had to learn, I had to be like, okay, cool, scheduling, that's an FSM. I know what those, I have scheduled appointments with my doctor. Like scheduling. So what is scheduling? Scheduling ends up being an IL integer linear programming problem, FSM extraction. I know what an FSM is. We all know what an FSM is. This binding thing is pretty straightforward. The hardest part of this, well, okay, so I have to replace Vitis. Vitis does stuff and then outputs the RTL, the digital design stuff. So what that amounts to is, so it's called generating RTL, but you got to generate registers, specs for registers. Yeah. I'm surprised you made it this far. Cheers. So you got to generate, like literally these things correspond to wires and bunches of flip-flops. So 31 flip-flops, 31 wires, right? And you have to generate IP bindings. So that means I got to plug in registers and wires to essentially bundle together bits of logic that drive a multiplier.
Question?
Yeah.
So this list of wrench wire, wire, is that then what, that's the direct control then of the FPGA?
Yes.
Or, okay.
Yeah. Okay, so you got to generate the bits and pieces. You got to generate the FSM. Hey, the transition's right. So I highlighted, hey, the way that this looks is, hey, if I'm in this state, go to the next state, state 2. If I'm in state 9, go to state 10. And you have to, so that's kind of simple. And by the way, I did this. Like, again, I didn't read a digital design book. I took the output of Vitis and I was just like, oh, what do I see that is repeated that I can see as it has patterning? And like these, by the way, these files, I didn't see that last message. These files are like millions of lines long. So you got to hunt and peck for this kind of thing. Anyway, so the schedule is implemented. Hey, when I am in this state, and I know that I'm in this state because this wire is hot, this wire has 1 on it, do these things. Feed 1 to this register. When I'm in this state, when I'm in any other state, sorry, this is control. This is their stupid protocol. When I'm in some other state, so state 8, connect these 2 registers, whatever. Okay, again, the hard part of this is actually not writing the RTL, the Verilog, whatever. That was annoying. That was whatever. You just like look at examples and copy paste. The hard part was making sense of this junk. Like what the hell is this, right? Turns out, by the way, so one interesting kind of useful kind of like thing to young people, if you're doing something hard, nobody's going to pay attention to you. I was asking questions, and there's a slide at the end of the small army of people that I got on the phone with to ask questions. And I was asking questions of this guy at Darmstadt in Germany. I told you about him. I was like, hey man, I need this. He has his PhD, his dissertation is on scheduling, something called modulo SDC scheduling. I'm like, hey bro, I have a really simple control flow. I just complete fall through linear, whatever. There's no branching, there's no looping, whatever. Doesn't it make sense that like a topological sort, blah, blah, blah thing would be the easiest way to schedule it? Because I was asking him what his theory was on why Vitis was taking so long. And he's like, yeah, that makes pretty good sense. And he's like, I don't really understand why, whatever. He didn't really dig into the meat of the question. So I went ahead and implemented this topological sort scheduler, whatever thing. Turns out that, hey, this has a name. It's ASAP scheduling, as soon as possible scheduling. This is like a known thing. Like I invented this thing de novo, but it existed. And more importantly, it existed in a tool that I could have used. Okay, so I implemented this. I was running with this for a while. Then like 2 weeks ago or 3 weeks ago, I wired something up. So there's another tool, it's an open source tool called Circuit that I can use to schedule things. Hey, now I have an integer linear program that'll, that corresponds to my neural network, give me the correct schedule for it. How many cycles does it run for? It doesn't give me the FSM, but it gives me, hey, this is the total overall end-to-end latency. There was a trick here with this PE dependency thing that I had to figure out because the ILP is huge. So the ILP for the smallest net is, I don't know, like 500,000 variables or something like that. And that stresses the solver, right? You can sit there because integer linear programs are also zero NP complete, NP hard. So you have to use a trick. Again, this is what, it's funny. This was a known trick that like is well known in the community, but I had to be like, oh, what if I did this? And then it turns out it's this trick that somebody could have told me, would have saved me some time. This third one is one that I hooked up like over the weekend. It hasn't landed as a PR. I'm going to try it soon. Okay, so the PE thing, I'm going to skip ahead, I guess. There's one thing, there's a grouping together of operations that you do. I've mentioned this to make the solver go faster. If you look at this representation of the for loop, you see something maybe obvious. I mean, it is obvious to people that do this stuff every day, but like you can parallelize this block of code. Hey, Tyler. Parallelize this part of the nest, right? So you have for all 3 of these loops, these are fixed, right? Like these 1, 2, 3, 4, they're not updated, they're not changed anywhere. So they're the same. these are the output pixels of the convolution. You can do all of these in parallel. And there's a really nice convenient representation in SCF that'll immediately tell you this, but I know, like, I saw this, oh, I can pull this out. This is a parallelization, obvious parallelization scheme. Why don't I group the logic on the board in this way? Okay, anyway. So this is, people call these processing elements. This is logically how I think about these. These are not actually physically oriented this way, but this is logically how I think about this as a grid of these call them whatever, processing elements that do only 4 things. They do add, mul, neg, and ReLU. The top 2 are really easy to do bitwise. Negation is just flip a bit. ReLU is a compare and then 0 and whatever. And the add and mul are actually IP, like you actually have to do the additional multiplication. Okay, so I'm gonna skip this. You have to, if you want to get a decent schedule, you have to implement a redux tree. Okay, whatever. Again, problem solved, right? Like you do all this work and it does nothing. You're nowhere closer to success. Okay, so then you have to be like, what's going on at the synthesis level? So once you get RTL, it's then fed through a thing that solves more math problems to actually place. So it maps your RTL to gates, right? Like none of the, I'm not gonna flip back because it'll lag. None of the RTL has stuff like carry adder. None of the RTL has stuff like flip-flop. It could, but it doesn't. So the synthesis tools, the logic synthesis tool will map from that to actual hardware. So this was the first, like, I got some kind of result and it was an unsuccess, like it worked. It worked. I got through Vitis and I was like, oh, cool, success. And then I hit the next wall, which is you can get all the stuff on the FPGA. So the left side says, I use the entire thing. The greens are adds, the reds are muls, the entire, so 99% utilization. I'm using all of the logic, all of the DSPs, all of the whatever, no RAM, but everything, right? And you're like, cool, I win, right? I'm under 100%. I'm at 99%, but I'm at 100%. And the way that they make big FPGAs is it's called stacked silicon integration. I don't know why it's called stacked. It's not actually stacked. It's actually laid out like left to right or top to bottom this way. They'll take individual dies, so like imagine like a whatever processor i7, and then just put them in like a column, and they route. So that it's easy to route intra route, right? Like on one die, it's very hard to route between. So one of the problems, sending Kyle these messages like, oh, the super long lines, there are not enough super long lines to map between them. So that was one issue. And then the other issue was like, I don't know why, again, black box, closed source, proprietary, it bunches all of these adds in here, creating router congestion. So this purple blob says you can't route this. There's high congestion, tough luck. Okay, so yeah, okay. So the next step of the problem was like I could get resource utilization under the limit, but I couldn't get routing to work. So what is routing? This is just an interesting picture. Like I didn't actually, you can fiddle with these switch boxes. They're called switch boxes, but just to illustrate at what level of granularity you're thinking when you're doing this stuff, those are literally wires, right? So there's like some kind of router switch box thing. My mouse is gone. In between the DSPs and flip-flops and whatever. And there's some kind of, it's a switch. It's like it's not a network switch, but it's something like a switch, and the wires cross it. And so you have a limited number of routing, like you have limited routing resources. You could run out of routing resources. And also to boot, that design, the one that I showed with the red and green splotches, had enormous power consumption. So this is, I showed like 4.5 kilowatts. I didn't realize it was actually 10 kilowatts. I don't know what that is, but that's like a generator powering this entire building or something like that on the chip the size of a, I don't know, the size of like a lunchbox or something like that. Okay, so what do you do, right? Like by hook or by crook, what you do is you relax your assumptions, you relax the constraints, you give yourself an easier problem to solve. So reduce the bit width that you're going to use to represent the operations. So in the previous one, I had FP16, which already is half of single precision 32-bit. Go down even further, go down to 8-bit. And why can you do this? What's like the justification for this? If you look at the exponents and the weights, so this is not the mantissa, the decimal part of the number. This is the exponent. This is literally like, hey, they only take on 25 values. In principle, the exponent can take on, in floating point IEEE, 754, like 32-bit, the exponent can take on 128 values, 256 values, something like that. And you use 7 bits for that, or something like that, whatever. I'm flubbing a little bit, but anyway, I don't need the full bit width that IEEE 754 floating point anything uses. I can use smaller bit widths for the exponents. Again, the mantises are a little weird in the weights, so I'm not going to cover that. But so there's a project from some university in France, INRIA, I think it's called INRIA, where they have a generator. You run their generator, it'll give you logic for doing floating point with 8 bits multiplication. And they have their own kind of slightly non-standard. It's not IEEE 754, but it doesn't matter. Okay, so that's one hack, one trick. The next one, so there are two like cute things in this project. The one is the abstract interpreter. The other one is this. The abstract interpreter is mine. None of the rest of the stuff is mine. It's just gluing stuff together. This is glue. This one I had to pull kind of, so like I had to pull something, had a, like was in the shower or on the toilet and had like a eureka moment. You don't want to reuse, you can't basically reconfigure the logic. You can say this block of logic does addition, this block of logic does multiplication, and you can't like dynamically during the run be like, okay, now this is going to do exponentiation. Now this is going to do division. You can't do that. It's frozen. You have to reflash the FPGA. You can get the addition blocks to do subtraction. So there's like a flip of a switch and it'll do subtraction, but you can't wholesale go from addition to multiplication or from multiplication to division or anything like that. So I want to represent everything in terms of additions, multiplications, ReLUs, and negs. That's easy. That's fine. The rels and negs don't cost anything. ReLUs and negs don't cost anything. Exponentiation, you can get from Xilinx, hey, this is a block of logic that does exponentiation. It's going to eat resources. And in this network, there's only one layer. There's a softmax layer that does exponentiation. So there's one slice, one time step that it has to exponentiate all the values in some activation tensor. And then the rest of the time, you don't need that. So if I devoted a bunch of resources to that, it'd be a waste of resources. And at the time I was like, oh, I don't have many resources. I'm running out of resources. I might have them now because I reduced the bit width, but whatever. So how do you represent exponentiation, which is a nonlinear function, whatever you want to call it, transcendental, in terms of addition multiplication? Hey, that's simple. Just take the Taylor series. That's easy. There's a division, a soft max. You take the exponents of all of the values, find the max, you add them up and then divide, right? So it's e to the x divided by the sum of the e to the x's. So you have to divide. Again, adding the exponentials is fine. The division is the one that like gives you trouble. How the hell? So right, this is easy. This is already addition and multiplication. How do you do division in terms of multiplication and addition? They're like, that's just like a kindergarten level arithmetic problem. No, you can't do that. Okay, this is kind of hard to explain. You can look this up on Wikipedia. There's a thing called the fast inverse square root trick, which blah, blah, blah was first implemented in Quake, this game called Quake, that uses like, it's kind of like folklore mythology at this point. It has this weird constant, like the source code for Quake was released and there was this crazy constant and then there was a comment underneath the constant, like where the hell did this constant come from? This is not that constant, by the way. But that trick works by basically approximating the log of a value by the integer cast. So if you look at the bits of a floating point number and you're like, this is just an integer. It's not, right? Because the layout of a floating point number is like sine, exponent, decimal. It's not an integer, it doesn't make any sense. But if you look at it like that and just pretend and squint, it becomes an approximation of the log of that number. And so you can fiddle with the algebra. Yeah, exactly. You can fast inverse square root on Wikipedia. Oh, was the inline comment? Yeah, exactly. Yeah. Gotcha. Yeah, so you can look at you can do some algebra. It's in the write-up of the paper. I don't know if I'm gonna leave it. It's pretty trivial. And you can do the same thing to do inverse. Instead of inverse square root, you can do inverse. Cool, now that I have the inverse, I can do the multiplication. I just multiply by that inverse number. The claim is it's like only 4% off. I don't really care. It's a one-time operation. And I do this inverse multiplication thing once. And that's it. This is the win. The win is that with FP8 and all these tricks, you get fully routed, fully placed. And then the question becomes, so this is like success, right? Like this is for me, like, oh my God, I'm finally done. The question is, what's the speed? We go back to the beginning, like how fast does it go? So there's a 10 nanoseconds here, which is kind of like confusing and deceptive. It doesn't run in 10 nanoseconds. This is that the clock cycle is 100 megahertz. So every 10 seconds, the clock ticks over. How many steps of that clock does my network take? It takes 3,000 steps. You do the multiplication, you get 30 microseconds. That's not the number I had in the paper, and it's not the number that I've been kind of like showing off, right? I was showing off 3 microseconds. So I am 10 off. Again, at this point, I don't care because this is, I think, as close to whatever as I can come without spending another 6 months. I mean, maybe I will, I don't know. But this is a win for me, but it's 30 microseconds. And I'll talk a little bit about where that 30 microseconds is spent. But so what are the measures of success? There's a slide here, right? I want the resource budget to be under 100%, want fully placed and routed. That's called design closure in the quote unquote community. I want timing closure. So that 10 nanoseconds says everything can tick on the 10 nanosecond interval, and there's no negative slack. So the way that the FPGA will like route signals and stuff is you have stuff that's far apart, and if it has to click over in the next 10 seconds and it clicks over too fast, the FPGA will include slack. It'll like say, hey, go around the corner and come back and then feed the ALU or whatever. So if you have positive slack, then you're a little bit, if you have positive slack, then you can take that off of the clock. If you have negative slack, then you can't make it. You can't make it fast enough. So, right, I'm right there on the head, 0.02 worst negative slack. Then the final thing is numerical accuracy. Hey, does this thing actually do what Bragg and N does, blah, blah. And so I don't have an answer to this. I had told Kyle, there's a way to kind of like guess at it, simulate it, blah, blah. I haven't done it yet. And to be honest with you, at this point, I don't care about that either. Whatever the accuracy is, it'll be an acceptable delta from the accuracy of Bragg and N, given that it works at, I don't know, like it's 10x faster, 100x faster, something. Okay, so so I'm way over, fine. But this question of like, Kyle, you asked me this question at the Argonne talk. Somebody asked Torsten this question: can this be automated? And here are 4 fancy ass theorems that at least inform my intuition. I don't have a proof of any of this, and I'm not a theory student, and so I'm never going to write one. But they make sense to me as informing like what my answer. So let's say you were like, I'm going to have a smart enough compiler that'll recognize these patterns of memory independence and blah, blah. Can I do that? Is that possible? And it turns out that you can't. Rice's theorem says, so there's the halting theorem, which says you can't decide, it's undecidable whether a program halts. Well, people are like, well, how about some other features, some other semantical features of like, hey, does the memories step on each other's toes and stuff like that? No. In general, right? Just in general, like for the generic program, can there be some other program that'll tell you, does this thing do X? The answer is no. That's undecidable. Beyond that, there's a bunch of NP complete problems here for scheduling, for route, for placement. All this stuff is NP complete. Even if you could have something that recognized your pattern or your code or something like this, it's still going to solve an NP complete problem. That's basically not good enough. So you can do better than the generic solver by like adding your own thinking juice to it. Okay, so you're like, oh, we do ML, right? We're going to train some kind of ML thing learner that's really smart and recognizes blah, blah. I'm going to look at a bunch of code, look at a bunch of RTL, billion samples, and I'm going to train a thing that'll give me the correct schedule, that'll give me the correct placement, whatever. And people are doing that, by the way. NVIDIA has some kind of paper where they did this. The no free lunch theorem says something like, so it's not what I wrote, but the understanding that I had of it before I looked at the definition was, you can't learn a distribution from samples of the distribution. So even if you had like some God-given distribution for what the spread of the logic is or what the schedule ticks are, just sampling from the distribution, no matter how many times, and this is theoretical, right? This is in the limit, asymptotically, whatever. You can't actually figure out what distribution is. Okay, fine. you're like, I'm gonna reduce the problem. I'm just gonna match, I'm gonna have like a library of placed and routed and scheduled things. And then I'm gonna take your code and I'm gonna chop up your code and I'm gonna match your code to the library of code of RTL and logic that I have. And then that'll be great. Maybe at the interfaces, I'll lose something, but in general, it'll be really cool. Well, this is graph isomorphism. So Babai, who's a professor here, this is literally what he's most recently famous for. You can't do that fast. And this is, by the way, is what a bunch of those, so that when I said alternatives, not really, this is what they do. They do like a matching process. So DACE, for example, does a matching process. Cerebrus does this. Cerebrus has a really hard time with this. And I know this not just like by imagining, but because the guy told me. The guy told me, hey, so when I was like debating one or the other at the beginning of the year, I had a call with the guy and he's like, our problem is the graph isomorphism problem, it's NP complete or whatever. I mean, he said NP complete, maybe subgraph isomorphism is NP complete, but Bai proved that it's quasi-polynomial. I don't know what that constant is, whatever, it doesn't matter. Future work. Okay, so this is like, maybe I'll get to it, maybe I won't, maybe I'm just gonna move to Hawaii or something like that. So if you look at the scheduling, so this is the timing summary. This is from the timing summary report. There's a bunch of stuff on here. The stuff that's highlighted is what you focus on. So this is for the design that had timing closure. Hey, the data path delay is the 10 nanoseconds. This is your goal, 10 nanoseconds. So I'm a little bit under, I have a little bit of slack. I could take a little bit off the top, whatever. Let's say I leave it at 10 nanoseconds and I put positive slack in. The interesting thing is, and this is well known in the quote unquote community, this is what Andrew Chen said, hey, the logic, the actual like compute is a very, very small part of the delay. It's the routing that for a lot of things, I mean, in these cases, and I cherry picked, right? These are the worst. I sorted by worst to whatever, least bad. And hey, 90% of the delay is routing, which means, so like I could run the logic in 1 nanosecond. And that's a gigahertz, right? That's a gigahertz in theory. And if I could run all the logic in 1 nanosecond, sorry, that's a gigahertz. That puts me at 3,000. That puts me at 3 microseconds. So what do? You flex like real, like human intervention. You place. You tell the thing that is not smart because it's general purpose. I want all the processing elements that are related to computing. Sorry, I want the processing element, which is like confined locally. Sorry, confined logically. It does ReLU, it does neg, it does add, it does mul. I want it to be geometrically placed, oriented, so that the delays are minimal amongst all its neighbors. Like, hey, I'm only talking to my neighbors. Don't put me all the way over here and then try to route from one corner to the other. Do this thing, be intelligent about where you place me. I know that you're not intelligent enough, but I have a high level view. So this is what Torsten wants. Torsten wants something a little bit different. He wants to place library nodes. So he has something bigger than adds and muls. He has a whole convolution, right? So he wants to place something that's bigger than this. He doesn't know how to do it. There's an API. The API sucks. The basic reason that this is like the challenge here with experimenting with this and why this isn't like a one afternoon experiment and getting it to work is because all the tools suck. The API is in Tickle. What the hell is that? Whatever. So this is I don't know. Maybe I'll get to this one. Yeah. Okay. So the last slide is. These are all the people. This is a small army of people that I have hit up for time and advice. Basically, each of these people, some of these, so nobody's recognizable, right? Like Kaz is on here, but you guys don't recognize any of these people. These are not nobody. Yadish, you remember Yadish, right?
I do remember well.
Yeah, right.
One of the most
So that was like an hour and a
awesome
half. There was an hour and a half of me asking this dude question who's
Well, really, it was you and him arguing with
That's
each other.
not true, bro. Anyway, it doesn't
It's
matter.
the most difficult conversation I've
It
ever
doesn't.
sat
It
and
doesn't
watched.
matter. I took an hour and
I still feel awkward.
I took an hour and a half of this guy's time. He's a seasoned, like highly competent FPGA designer.
And you told him what he told you, and he said, "I never told you that," and you just kept
He
going.
gave me advice and I learned
But
things from.
you went back and forth like 5 times.
Why are you belaboring this?
Yes, you did. So that's actually what happened. I'm not,
Fine,
I
whatever.
exaggerate things, but that's actually what happened.
Fine, whatever. Anyway,
Did that happen? Did that happen like that?
it didn't happen like that.
Yeah, you did. You told him like you said this, and he
I
said,
have a
"No."
video, I think, actually.
Find it. Pull it out.
The rest of these people. So Han Chen is the kid at UIUC, right? He's a grad student.
Like that, actually, when he's saying that. It's exactly like that, except with a guy we didn't know.
Okay, anyway, nobody knows in this room who these people are. I might give this talk later in front of these people. So there's a community open design meeting. So all these people are in that community and I'm gonna like, so that's the point of the slide. And okay, cool. So that took 90 minutes, but thank you for indulging me.
Yeah, we're getting faster. Very nice, Max. Well, I mean, that deserves like. Absolutely.
Yeah.
Yeah,
Okay. The end.
yeah, that's very impressive. Max.
Questions? I mean, it's,
You've convinced me
Yeah.
that there were 7 circles of hell.
yeah,
Yeah,
exactly.
there were some circles.
Yeah. And I didn't even talk about like OOM shit, like,
Yeah.
oh, I need like 200 gigs of RAM, like 200 gigs of
But
RAM,
that
and
you
like,
just sold by getting bigger machine. after
yeah,
bigger
fine, but I
machine.
had to like beg and plead and like, you know, walk, go door to door asking, I didn't get RAM. I, you know, I have a friend at UF who has this cluster that is like his own cluster that he got money from DARPA for. Like, I spent $100 on AWS thanks to Kyle, and then I was up. shit
So I
creek.
get
The
a bill
Theta
for it?
GPU login nodes have half a terabyte of RAM and are never being used.
But what's the, so this is the thing, right? Like,
that's fine.
what's the maximum job time?
Well, the
They're
login
login
node,
nodes,
there's no
there's
job.
no maximum.
Oh,
time.
wow.
They don't get shut down.
But they're
every 2
sorry,
weeks.
but-
I've left stuff running on for like 48 hours
What-
before using like 300 gigs of RAM and never been complained
What
about,
kinds
so-
of processors? It's
Uh,
a Theta
AMD
nonsense.
No, it's the
Epic.
login, yeah.
Are you
Yeah.
serious?
Yeah, this is my secret, so.
Login
I
node
don't tell
computing
everyone
and
about it,
ALCF is
okay?
like.
I did not know this. And I suspect if you did it regularly, you'd be in trouble.
How many login nodes are there? They're like thousands.
There's only 2
Oh.
GPU login nodes.
No,
but
no, I
by
don't need
default,
GPU.
people go onto the Theta login nodes. They don't go onto the Theta GPU login nodes.
How many, I don't need a GPU. How many 500 gig?
Well, that's what I'm saying. They're just login nodes. There are no GPUs.
Okay, how many nodes with 500? gigs?
Two.
Two. Okay, yeah. So that I would immediately come up on somebody's radar. Why is there a 200 gig?
Dude,
like
I
a
literally
task?
do this all the time. Whenever I'm encoding data sets, which takes like a stupid amount of RAM, that's what I do it on.
Like, as long as you.
Would have been
only
nice.
limit yourself
Yeah,
to,
I
like,
mean,
half the
yeah. I should have like.
Always start with Greg if it's a resource question. He seems to find a way to get a supercomputer to himself
Yeah.
regularly.
Uh,
Does
Okay.
anyone have any questions in the negative 28 minutes we have left?
worst negative Slack, 28 minutes.
I'm amazed everyone's still there. I feel like we should poke them and see if they're still actually.
Nick is still there. That's amazing. Nick is still there.
I mean, the fact that you.
I'm alive.
Who's
Good,
that?
okay,
Is
that's-
that
that's
Jim.
Jim. Life, that was Jim.
Hey, man.
Nice job, Max.
We've talked about this every week or two and it's been a hard
Yeah.
slog for sure.
Yeah.
It's been an impressive, like, I mean, I know nothing about this. You know, you started knowing a
No.
little bit more than me and now you're an expert in this area.
I'm not,
So
I'm not. I
I
know,
think- I think you know more than probably most of those names at the end.
no.
I think so.
The
I'm blind faith in Max.
I missed. the
Blind
beginning.
faith.
What is this presentation for? Just for the user group? Or is this just a global size
This is
presentation?
just GLabs.
This is practice.
That's more slides than my thesis.
It was also a longer.
I was gonna say, this could be a
Yeah.
thesis.
We just gotta get some.
You had a
numbers
much
published.
stricter time. limit for your
Yeah.
thesis.
Question about the routing stuff.
Yeah.
Is if you had a larger FPGA with more.
Yes.
Programmable
The answer is
gates, could you
Yes.
replicate individual components?
Yes.
Such that whatever the data locality is, could be done on that replicated component?
Yes,
on either side?
That is actually one of the optimization passes that the router will do. If you have a high congestion
Gotcha.
net, it will, and you can force it. So I force it, you replicate that register.
Oh, okay.
So the thing that I didn't talk about were the costs involved here. So the target is so those pictures were of a particular FPGA of their Alveo 280, which is their data center thing. They're trying to, break into like take some of the market share from NVIDIA. Bullshit. That thing costs $9,000. Like, and it's way shittier as far as compute than as far as like batch compute, latency, throughput, whatever, than a 3080 Ti. So you're paying a ton of money for what? The next step up is $40,000, which is fine. Like Fermilab has that kind of money, but
G-Labs doesn't.
and I don't, right? Like I have a little $100 part. Yeah.
So he sells his company for $1 million seed.
What? No, there's no company here.
Okay, no Max company.
How do I get the video from Ben?
Yeah, that's why I took over as host. I think I can get it. Let me stop this and see what happens.